Okay, so as we start here, we're going to take a look at our new unit, quadratics. So we're going to start by graphing our new basic parent graph. So before we had our last parent graph was y equals absolute value of x. It always gave us a v. Now we're going to do something very different. So let's look at our new parent graph, y equals x squared. If I go through and I make my basic t-chart for x and y values, then we'll be able to see some basics of what this is going to look like. So if I plug in a -2 squared is 4, -1 squared is 1, 0 squared is 0, 1, and 4. When I go to graph this, what we're going to see is a fairly distinct, almost U shape. So feel free to use a calculator, use Desmos, whatever tool you might have available at home to help you graph. If you have nothing else, learn to graph it by hand. It is a useful skill as well. Let's see if we can help make this not repeatedly autofocus. Okay. So as we go to plot these points, 1, 2, 3, 1, 2, 3, let's see what this graph ends up looking like. So 0, 0, well, that's easy enough. And then we have 1 and 1, -1 and 1. We have 2 and 4, -2 and 4. And we get this, what almost looks like a V at first, but it's curving. So when you go to draw it, make sure your line's going straight across the bottom here. And then it's coming up. And we're going to get kind of this U shape. This is our standard parabola. Now, when we look at these, there's certain key points that we really want to look at. So first is the tip of this parabola. That's the vertex. In this case, our vertex is the point 0, 0. So it's always the tip of the parabola. Notice that the parabola is mirrored. So when we talked about symmetry, the parabola is pretty much the same on the left and right side. So we actually have an axis of symmetry here. And in particular, the axis of symmetry is the line going right through the vertex. So in this case, we have a straight up and down line. So x equals 0 is our axis of symmetry. This is our basic parent graph for a parabola or a quadratic. So any kind of function that has a highest power of 2 is a quadratic. It's going to be shaped kind of like a U. And this U shape, the generic term for it, is a parabola. So this is what we're going to be spending all of our time working with on this next unit, parabolas. Now, we have a whole bunch of different equations that involve parabolas. So here's our first one. The generic equation for any parabola is y equals x squared plus bx plus c, where a, b, and c are just kind of whatever coefficients you have. The only rule that we have for them is a can't be 0, because if it was, then it wouldn't be a quadratic anymore. We just have like 2x plus 1. We'd be back to a linear function. So this is our generic equation for a parabola. Now, just like when we talked about the absolute value graphs, a lot of these numbers give us some good information. So in particular, if that a value is positive, if it's greater than 0, then the parabola is going to open upwards. If our a value is less than 0, our parabola is going to open downwards. So just like with the absolute value graph, that positive made it up or made the v open downward, same thing here. If that a is positive, we'll have a parabola going up. If the a is negative, we'll have a parabola coming down. And still, just like when we talked about the absolute value graphs, if we just look at the size of that, if it's bigger than 1, then our whole parabola ends up being narrower. We'll actually squeeze it in, it'll go in faster. If that's less than 1, so if we get like 2/3 or a half or a point or something like that, then the parabola is going to end up wider. So again, we're seeing that same kind of mirror. Couple more points, one really easy and then one not so much. So our C value, that last point is always the y-intercept. So that always tells us exactly 1 point on our graph each time we do it. In this case, up here, there was no C, so it's 0. And sure enough, we intercepted the y-axis right here at y equals 0. Our final one, and this is our first formula, actual that we'll have to do calculations with besides this guy, is trying to find our vertex. So the vertex is usually the most important piece of information that we have when we deal with a parabola. In the case of a generic form, it's kind of hard to just look at it and tell what's going on. So in particular, the x-coordinate for our vertex is negative b over 2a. That is also going to be, because that tells us right where that vertex is, that's also going to be the equation for our axis of symmetry. So our axis of symmetry is also going to be negative b over 2a. So this is our first kind of formula that we really need to remember, that negative b over 2a is really, really useful. I know I'm giving you a lot of just theory right here at the beginning, but we're going to do a couple graphs. All right, so let's actually try graphing. So let's say they gave us something like y equals negative 1/2 x squared plus 3. And we needed to graph it and label all of the important information on it. Okay, so just looking at it, we know a couple pieces of information. It's y equals x squared, so we know it's going to be a parabola. It's going to be our U shape. We have a 1/2 out front, so we know it's going to be wider than normal. We know it's negative, so it's actually going to be going downward. So when I go to identify these, the first thing I need to figure out is the vertex. So where is this whole parabola starting? So our vertex is negative b over 2a. That's our important piece of information. So if I look at this and I compare it to the generic function ax squared plus bx, not bx squared, bx, plus c, and I look at what we have, I can identify each of our terms. So a in this case is negative 1/2. B, there's no x value here, so that's b is 0, and c is 3. So I can actually plug in my vertex for my x value and see what that x value is. So let's try it out. So negative b would be negative 0 over 2 times a. That's 2 times negative 1/2. That gives me negative 0 over negative 1, which is 0 over 1, which is 0. So the x-coordinate of our vertex is 0. So now I know my vertex is going to be 0 something, but I need to find out what that 0 is. So to find out, I'm going to plug that right back into the function. So if I plug in 0 in for x, it gives me negative 1/2 0 squared plus 3, and that's just 3. So my vertex is 0, 3. So that's the first point I'm really going to plot on my graph. Zero, 1, 2, 3. There's my vertex. Now, when we look back at our original parent graph, we have a very specific pattern. Because we're squaring things, if I go over 1, here's a distance of 1, and then I square that, I go up 1, because 1 squared is 1. If I go over 2 units, 1, 2, 2 squared is 4, that's going to match how far up I'd have to go. 1, 2, 3, 4. So over 2 units would be up 4. So if we went over 3 units, we'd have to go 3 squared. We'd have to be all the way up here somewhere at 9. So I'm going to use that same basic pattern from when we plot points to figure out where the points would be. So normally we'd go over 1, down 1, and down because it's a negative. but since it's negative 1/2, I'm going to go over 1, down 1/2. If I went over 2, 1, 2, normally on the graph we'd go down 4. But now we're at 1/2, so I'm going to go down 2, 1, 2. Same kind of reasoning over here. Normally it's an x squared, we'd go over 1, up 1. Since it's negative 1/2, I'm going to go over 1, down 1/2. Now if I'd go over 2, normally a parabola would then have me go 4, but since it's negative, it's down, and since it's half, it's 2. 1, 2, 1, 2. So my parabola is going to look something like this. So we're pretty good here. We have our basic shape. I'm going to label the vertex of 0, 3, and I'm going to label the axis of symmetry. So the axis of symmetry is the line going right through the vertex. So in this case, my axis of symmetry is x equals 0. So I've identified the axis of symmetry. I've identified the vertex. I've plotted at least 5 points to show a parabola. The vertex and then 2 more points on each side. That is sufficient to show the whole thing. So when I go to grade, this is kind of what I'm looking for. Have you clearly labeled the vertex? Are you showing kind of where the axis of symmetry is? You can just write the equation next to it. And do you have at least 5 clean points on your graph? All right, so we have our basic graph here. Now, as I look at these parabolas, those vertexes also tell us something important. They give either a maximum or a minimum value for the parabola. So notice that when I look at this parabola here, it comes all the way up to this point and it never gets any higher than that. It goes all the way back down. So if we were to talk about this in terms of range from those previous lessons, our range would be negative infinity to 3. We start from way down below, we come up to reach 3, and then we go way back down. So this graph here, the vertex is actually giving us a maximum value. It never gets any higher than that. So when we go to look at parabolas, our maximums and our minimums are gonna be the vertex y value. So in this case, we'd have a maximum value of 3. Going back to our original parabola, our parent function, we'd actually have a minimum here because it goes up forever, and it comes all the way down to just 0. So this parabola actually has a minimum value, and its minimum is 0. So when we go back and we look at our equation, then, it's flipping in the wrong direction. What we need to do to determine if it has a minimum or maximum is really just say, is it going upwards or is it going downwards? If a parabola is actually opening upwards, if we have a standard shape, then it's going to have a minimum value. And that minimum value is the y value of the vertex. If the parabola is upside down, if we're getting this upside down U shape instead, then we can know that the parabola is going to have a maximum. It comes up and it reaches a maximum point, and that value is just the y value of the vertex again. So this allows us to find a minimum or maximum just by looking at an equation. So let's actually try that out. So now let's say we have some horrible ugly equation, y equals 4x squared plus 16x minus 3. And we need to know, does it have a minimum or does it have a maximum? And then what is that minimum or maximum? All right, so we look at this, I compare it to our general function, our ax squared plus bx plus c. So in this case, my a is 4, my b is 16, and my c is negative 3. Since a is 4, it's a positive value. This parabola is going to be right side up. So since it looks like this, we're going to have a minimum value. So this function has a minimum. To find the minimum, we need to find the vertex. So I know that my vertex is going to be x equals negative b over 2a. So that's negative 16 over 2 times our a value of 4, which gives me negative 16 over 8 is negative 2. So the x value is negative 2. That's the x value of our vertex. To find the actual maximum or minimum now, I'm going to plug that into our function to find out what we get. So my y value then is going to be 4 times negative 2 squared plus 16 times negative 2 minus 3. So that gives me 4 times 4 plus negative 32 minus 3. So that's 16 minus 32 minus 3 is negative 19. So this function has a minimum value, and that minimum value is negative 19. All right, so as we go to graph them, be careful. Show your points. Make sure that if you actually graph it, you're showing the vertex plus 2 more points on each side. If someone asks you, does the function have a minimum or have a maximum, all we need to do is we look at the a value. Is it positive? Then it's right side up and we have a minimum. If it's negative, then it'd be upside down, we'd have a maximum. And to find that minimum or maximum, we're going to find our vertex. So we say x equals negative b over 2a. I plug in those a, b, and c values into it, and I find the x value for the vertex. I plug it back into the function, and I find the y value of the vertex. The y value is the minimum or maximum value. And again, in this case, since it's right side up, it will have a minimum. That minimum is negative 19. All right, so that was our first form of working with a parabola, is it can be in standard form. Standard form is not that easy to work with. So what we're going to look at next is an easier format to work with this type of function. So standard form, our most basic form, is our y equals ax squared plus bx plus c. But if you think back when we worked with our absolute values, we were able to write it out in terms of like h's and k's, and that gave us a whole bunch of useful information about it. So let's kind of recreate what that would look like. If we start with our y equals x squared, we can still do all the same transformations that we did before. If I add a value at the end, it'll move it up. If I subtract a value, it'll move it down, just like when we did the absolute values. If I put a letter inside, if I add something inside the function, that moves it left and right. The a value we already established changes kind of the shape. Is it upside down? Is it right side up? Is it wider or narrower? So if we put all that together and we think in terms of what we did with the absolute values, we can give vertex form as our next. So vertex form is y equals a times x minus h squared plus k. So this looks very, very similar to what we did in Unit 2. Look at this, y still tells us whether or not we're shifting, are we going up or down? Is it narrower or wider? And then our vertex is actually just the coordinate point hk. So it's much easier to get a graph out of. So let's try taking a look at this one. Let's say they say we need to graph y equals, let's do kind of something horrible, negative 1/4 x plus 2 squared plus 5. So now we have a new function that we need to graph. Since it's not in ABC format, it's not in this format, we can use vertex format instead. So as I look at these, I can identify a couple things. First of all, my vertex is hk. So my vertex is negative 2, 5. Notice in the original function, it's x minus a value. So if it's a plus, that means our h has to be negative. So it's always the opposite sign. Our k is just whatever's there, so I know where the vertex is. We know that the parabola is going to be upside down because this is a negative, and it is substantially wider. It is 1/4. So now I have some basic ideas of points. I'm going to go ahead and graph them out. So negative 2, 5 is our starting. Negative 1, negative 2, negative 3, negative 4. 1, 2, 3, 4, 5. So we're starting at negative 2, 5. So there's my vertex. Ooh, if we know the vertex immediately, that means we also know the axis of symmetry. Our axis of symmetry would be x equals negative 2. And I could even sketch that little axis of symmetry that would have to be mirrored for it. Okay, so we know that. Now, I'm going to apply some of those rules again to determine where their points are. So again, a parabola normally goes over 1 and up 1 in each direction. But we're upside down. So instead of going over 1 and up 1, we're going down. And it's a fourth of that. So over 1, down a fourth. Over 1, down a fourth. So this is much wider. Our next step is normally we'd go over 2 and then up 4 units, but we're negative, so we're going down, and it's a fourth of that. So we'd go over 2, and instead of going down 4, a fourth of 4 is just 1. So there's my second point. Over 2, down 1. So this is now the 5 required points to sketch it, and I have a really wide parabola here. So again, I've shown the vertex. I know it's upside down because it's negative. I know the axis of symmetry because I know the vertex is just negative 2, 5. And then I can find my next couple points. So I have my graph for my parabola. All right, there is one other format that we will often use when graphing parabolas, and that is the intercept form. So intercept form is a little bit different. With intercept form, what's happening is we have something where we know where it's touching the axis, and that's kind of all we really know. So if I have the parabola touching right here at, say, 0, 0, and I have the parabola touching here at, say, negative 4, 0, then we know the intercepts. So this is a method of graphing the parabola based on the intercepts and the vertex. So the generic formula for the intercept form is, in this case, it's a little bit different. So we're actually going to still have our a value. They'll still give us useful information. Then we're going to have x minus p and x minus q, where p and q are simply these intercept points, whatever they might be. So p and q are both x-intercepts. So that's simply giving us where they're hitting. So let's try looking at something like this. So maybe they give us an equation, something like 2 times x plus 3 and x minus 1. Okay, so we have a parabola. I know it's right side up and it's going to be narrower because we have a 2 value. Now to use the intercept form, what I'm going to do is I'm going to identify what p and q are. So notice in the intercept formula, it's a minus, just like when we had with our h. So here my p value is negative 3. My q value is positive 1. That's telling us 2 of the intercepts. So positive 1 is one of our intercepts here, and negative 3 is another one of our intercepts. So 1, negative 2, negative 3. So I know these 2 points are on my graph. 1, 0, and I know that negative 3, 0 are both on it. Our problem is this isn't enough. We need more points. In particular, we need the actual vertex. We don't have it in a format that's easy to get the vertex. Not the way we did it before, where vertex was negative b over 2a. But because parabolas are symmetric, our vertex is going to be right in evenly in between these two. So what we're going to do to find our vertex is we're actually just going to average the P and the Q. So the X value for my vertex is going to be P plus Q over 2. It's exactly in the middle between them. So in this case, my vertex is going to be at -3 plus 1 over 2. Is -2 over 2 is -1. Which graphically, if we look at it, 1, 2, 3, 4, yeah, it'd be at -1. So I know my vertex value is x equals -1. There would be my axis of symmetry. But we still need to know the actual vertex. So I'm going to take my -1 and plug it back into my equation to find my y value. So y equals 2 times -1 plus 3, -1 minus 1. Give me y equals 2 times -2 is a -8. So it'd be way down here. 1, 2, 3, 4, 5, 6, 7, 8. Our vertex would be way down here. I think I'm already off the camera here. So our parabola is going to end up looking something like that. If it is in intercept form, we only need the 3 points, the 2 intercepts and the actual vertex. And here our vertex was -1, -8. All right, so we've looked at a bunch of different ways to graph it. We've seen kind of how we can put it together. So just kind of recap and kind of look at each of these things. So our basic parent graph is y equals x squared. That was our most basic parabola. We are talking about quadratics, which is something you should have talked a little bit about in Algebra 1. Honestly, most of this should be pretty familiar. We have standard form, which is our y equals ax squared plus bx plus c. We have vertex form, which is actually a little bit easier to work with, which is our y equals a times x minus h squared plus k. And we have our intercept form, which is our y equals a times x minus p times x minus q. So all these 3 ways are different ways of representing parabolas. They'll get us to the same point. What is usually going to determine which one is easier to use is honestly kind of what do we have to work with. Graphing-wise, vertex formula is typically about the easiest I find to work with all the time. If intercept doesn't come up very often, honestly, but when it does, if it's already an intercept method, that's really easy to work with. Standard is the least user-friendly. We have to do more work. You can't just look at it and kind of tell what's going on. So that's kind of my tiering of which ones I prefer to use. All right, so let's take a look at one word problem as a way to end this off, and then we'll finish up. So let's say, for example, we're looking at a suspension bridge. Here's my point of reference, so that's like the 0, 0. And the bridge is, let's say that the support struts for the bridge are 307 feet tall. So we know this distance from here to here is 307 feet. We know this distance from here to here is 307 feet. And if you've ever had the chance to drive across a suspension bridge, it's very similar to a parabola. It's not quite exactly, but it's pretty close. So the cables come down and do something like that, assuming I could draw a nice curved line. So that would be our vertex if we were looking at this as a parabola. Now they went through and they modeled it, and they tell us that the equation of this parabola is 1/7000th x minus 1400 squared plus 27. Nice random amount there. All right, so this is what we have. What other information could we get about this? Well, honestly, there's quite a few little interesting things we could get. I guess I should actually, hold on. Let me add the road itself. Now this is pretty good. It's just my bad graph. So when we look at these, we have a bunch of information. So we have cars driving across the bridge. I feel like I'm drawing a car from like elementary school here. There we go. So cars are traveling across the bridge down here. We could figure out the distance between the two supports, actually. So let's take a look at this. We know it's right side up because this is positive. We know it's way, way wider than normal because this is a ridiculously tiny fraction, 1/7,000th. We know the vertex is up at 27. And we know the vertex is moved right 1,400 points, in this case feet. So right here, this point is 1,427. So the bottom of these lines is only 27 feet above the road. And the exact middle is 1,400 feet. So if I wanted to find the entire distance across these, well, this is 1,400 and that's 1,400. So the whole distance between the two supports then would have to be 2,800 feet. If they asked us how high above the road does the line come down to, well, that's just our y-axis. So it's only 27 feet. So obviously I did not draw this well enough to scale. This guy would be like way up here then. So we can get a lot of information just from looking at kind of these parabolas as we do it. I'm not going to ask you to create the formulas typically at this point. I will provide you a formula and then ask you to analyze it if we talk about a word problem. All right, so today's homework is mostly just graphing and analyzing. I'm going to ask you still to tell me how does a graph compare to the original, just like we did in previous lessons. So if I were to go back to this one and I wanted to say in words, this graph was shifted left 2 units, up 5 units. It is upside down. It is wider than normal. So just like how we described the absolute values, I can use the same thing. I'm almost always going to ask you what the vertex is. So here our vertex was -2,5. And I'll often ask what the axis of symmetry was. So our axis of symmetry was x equals -2. If I go back even earlier to one of our previous examples and talk about it verbally again. So let's say going back to this guy. Okay, so this one, we had our -1/2 x squared plus 3. So if I wanted to describe in words what happened to this, it was shifted up 3 units, made upside down, and then it was wider. Upside down because of the negative, wider because the a value is less than 1. Up 3 units to where our vertex is. My axis of symmetry is x equals 0. So that's kind of what I'm looking for. It's very, very similar here at the beginning to what we did when we first started talking about absolute value graphs. Draw neatly, it'll help.